super spectacular and blow people away. And what you see on the left side is the ground-based image of a simple star field. The star toward the top, the uppermost star, is really a binary star, so it should have been nicely resolved into two separate stars. And on the right is the corresponding Hubble image of that same field. And I think people looked at each other and scratched their heads and said, is that supposed to be how it looks? And I think everyone knew in their hearts this was a bad sign. So next graphic, please. So the problem, as Ed mentioned, is that, and of course, Hubble is not made of lenses. So I'm representing the whole Hubble telescope here with a very simple lens just to illustrate a simple point, that light is coming in, parallel light is coming in from a very distant source in the universe as a beam and intersects the entirety of a lens in this case. And the beams that come in around the periphery of the lens are focused, brought to a focus by the lens at one point. And the beams that come in closer to the center of the lens are focused at a different point. And in a spherical lens, in a spherically aberrated situation, there's no way you can adjust the focus to make all those points come to a sharp focus at the same time, at the same place. And consequently, you get a blurry image, as you see with that upper A. On the other hand, a perfectly produced lens, performing as it's supposed to, brings all of those beams, regardless of where they come through the lens, to the same focal point. So you get a very clear, sharply focused image, and the A has gotten clearer there. Next image, please. Okay, this is a layout of our telescope, and of course we have mirrors, not lenses, and so light comes in from distant astronomical sources through the opening, the aperture of the telescope there at the left, is reflected off our 2.4 meter primary mirror, which is the red structure you see there, is focused back onto the secondary mirror, which is about 1/3 of a meter in diameter. And from there, the light is relayed back through a central hole in the primary mirror to the focal plane in the back, where all the scientific instruments and electronic sensors are supposed to get this beautifully focused, crisp field of view of the object being viewed or the star field being viewed. And the problem, as Ed described, was that red mirror was ground down too much glass was taken off. So as in the previous slide, all the rays of light that are coming in at the periphery do not come to a focus at the same position as the rays of light that come in closer to the center of the mirror. It's very classical, very simple spherical aberration. Any amateur astronomer knows to worry about it, and we didn't. Next slide, please. Okay, so that's how the spherical aberration worked, and now pretend the mission is over, the 1993 mission is over, WFPC2 is in, COSTAR is in, and I want to give you one astronomical example of how the two have worked together. This is a glorious image taken with WFPC2 of a portion of the giant elliptical galaxy M87. It's in the Virgo cluster of galaxies. It's not all that far away from us. And this galaxy is famous for being a strong radio source and for having powerful emissions coming from its very nucleus. And you can see that that jet that's been emitted and all the globules in the jet that you can see illuminated there. And that's a beam, principally electrons, coming out from the center of the galaxy, the nucleus of the galaxy. And forever, astronomers have thought there must be a supermassive black hole as the central engine of what's going on in this galaxy, but they couldn't prove it. And then when we got Hubble up and we wanted to address this issue, we still couldn't prove it because Hubble could not get a clear image. But after the 1993 mission with WFPC2, at last we could get a super sharp image. And go to the next chart, please. You can see we've zoomed in now on that nucleus. We see a very bright disk of gas and dust that's rotating, as a matter of fact, at the center. You don't see a black hole because it's black, but you can see the disk of material that's in rotation around it that is compressed and heated and emits light. Okay, so WFPC2's beautiful resolution at our disposal for the first time allowed us to really resolve what the center of this nucleus looks like. And now comes the COSTAR part of the story. Next chart, please. And the data you see, the two peaks, you see the lines drawn there on the left, one red and one blue. That's the kind of data that COSTAR allowed the faint object spectrograph to acquire. Those are spectral emission lines. The red line is coming from the part of that disk that's moving away from us in rotation. The blue curve is on the part of the disk that's moving toward us in rotation. And the separation between those two representations of the same emission line tell you how fast the disk is rotating. And what we learned was, in order for that disk not to come flying apart because of essentially the centrifugal forces in the rotation, there had to be a mass, a source of gravity, 3 billion times the mass of our sun concentrated in a very small volume. So for the first time, WFPC2, followed by complementary observations by COSTAR helping faint object spectrograph, demonstrated the existence of a supermassive black hole at the center of a galaxy. So that kind of thing just made us all deliriously happy. It got just one major scientific discovery after another coming online in rapid succession. And the hero of this story is John Trauger. And John, tell us how you did it.
The hero of the story is a team that did a wonderful job. I was proud to be a part of it. Okay, so we're going back again. We're doing this history all over again. It was back in 1990. We had these images. We were puzzled. Over at JPL, we had the images, and we were beginning to think about what we were going to do. What was the problem? A senior scientist named Aidan Meinel walked by. He was interested. He was curious. He took a look at the images that we had, those first images, and he immediately recognized the signature of spherical aberration. For me, that was my introduction to the world of spherical aberration. And it said that no amount of alignment or focusing could ever fix the telescope. We would have to go back and do something fundamentally different. We would have to devise a correction. And it happens I bumped into Aidan Meinel again a few days later, and he said, almost continuing that conversation, and by the way, if the spherical aberration is on the primary mirror, take a look at those little mirrors in your camera in WFPC. Changing the shape of those should fix it. Well, that was a very intriguing thought. I spent the next week down with the optical engineers. We had a complete model, optical model of the telescope and our instrument, and we played out all the scenarios we thought could be relevant. Maybe the spherical aberration is on the primary. Maybe it's on the secondary. Maybe it's on both. And we played out all the scenarios we thought were realistic, and we found a solution for each one of them. And each one of them involved replacing one or two mirrors, one or two sets of mirrors in our camera. So we were set, and off we went. As has already been mentioned, this was the middle of June, and we were on our way. I have an animation which will illustrate how that correction works, but it goes pretty quickly. So let me mention, say in advance, what you'll see. It's like an X-ray. It's a cartoon, but it's an X-ray.